In this video, I'm going to continue talking about the mathematical background for this course. So the first concept is called the basis of vector space. In the previous lecture, I talked about what is a vector space. It's actually a span of a set of vectors. For example, if I give you x1, x2, the vector space of x1, x2 is given by the span of x1, x2, which is the span is defined as alpha 1 x1 plus alpha 2 x2 is a linear combination of all the vectors with a weight, with a different weight assigned for different vectors. Okay, so a set of linear independent vectors is called a basis if every vector in the space can be expressed as a unique combination of the set. Okay, which means we have a span. Okay, let's say we have a span over here. We want to find a set of vectors that can be used to represent any vector in the space. Okay. For example, if I give a vector space which is a span of x1, x2, x3, x1 is 1, 0, x2 is 0, 1, x3 is 1, 1. So first of all, we talk about the dimension. The dimension of the span is 2. Okay. So the dimension of span is determined from the previous lecture. If you remember, the dimension of span is given by the maximum number of the linear independent in this set that created this linear space. So which means how many of these vectors of x1, x2, x3 are linear independent. So apparently x3 can be written by the sum x1, x2, which means derived from x1, x2. So x3 is not independent of x1, x2. And x1, x2, if you check, they are linearly independent. So the dimension of the span is just 2 because there are only 2 linearly independent vectors in the space. So a basis is quite straightforward in this sense. You basically trying to figure out those vectors in this x1, x3 such that they are linearly independent. There will be a basis. For example, because x1, x2 they are linearly independent, so x1, x2 is a basis. Okay, of course you can also say x1, x3 is a basis. So the basis typically is coming from these vectors. Okay, from the vectors that created the linear space, and they must be linear independent, of course. Okay, so x1, x2 is, so x1, x3. Why x1, x3 also linear? Because x1, x3 are also linear independent. Okay, and x2, x3 is only. So here we can see the number of vectors in the basis is equal to the dimension of the space, the linear space. They're equal. So if the dimension of the space is 2, so you have 2 vectors in the basis, and this vector must be independent, of course. Okay. And here's an example. For example, I have x1 is 1, 2, 0, x2 is 1, 0, 0, x3 is 2, 4, 0. Okay, so here the vector space is defined by the span of x1, x2, x3. This is the same as alpha 1, x1 plus alpha 2, x2 plus alpha 3, x3. Okay, the dimension of the span is the number of linear independent vectors in this of the 3. So how many of these are linear independent? The maximum number of vectors that are linear among the 3. So 2. Because x1, x2 is a linear independent. x3 is derived from x1, is twice of x1, of course, so it's not a linear independent of x1, x2. So the linear basis of the span is, you can see x1, x2, okay, the linear independent. Also, you can see x2 and x3, okay, the linear, but x1, x3 is not a basis because they are independent. Okay. The next concept is orthogonal and orthonormal. So orthogonal, here's a definition of orthogonal of 2 vectors. The vectors x1, x2 are orthogonal if x1 transpose times x2 is 0. So next we talk about what is transpose. x1 transpose, so typically here when we mean the vector is a column vector, so x1 is sort of something like 1, 2, and 3, for example, and x2 is another one. Let's say 0, negative 1, and 3, for example, whatever it means. So transpose is you change row to column and column to row. If this is a column, you change it to row. 1, 2, 3. So this is x1 transpose. The product is defined as x1 transpose times x2 is 1, 2, 3 times 0, negative 1, 3. So this is just you do entry-wise product. You first one times first one plus second one times second plus last one times last one. You do entry-wise product and you compute the sum. So it's 1 times 0. So it's 1 times 0 plus 2 times negative 1 plus 3 times 3. So we can compute the value is 1 times 0 is 0. 2 minus negative 1 is times negative is negative 2. Negative 2 plus 9 is 7. So it's 7. Alright. So the vector and orthogonal means if x1 transpose times x2 is 0, so they are orthogonal. Okay. Orthogonal you can also mean this is perpendicular. You sort of write over here if I have x1 x2. So typically at 90 degrees. Of course, this is only for 2D and 3D space. For high space, I don't know how to draw that, but they're also perpendicular. You can solve it in that way. For example, if x1 is 1, 0, x2 is 0, 1. So x1 transpose times 2 is 1, 0. So you change the row column to row x1, 0, and this x2 you remain the same as column is 0, 1. So you do 1 times 0 plus 0 times 1. So you get a 0. So they are orthogonal. It's sort of like this. Orthonormal is derived from orthogonal. So vectors x1, x2 are orthonormal if still we have the problem x1 transpose times x2 is 0. And also x1 transpose times x1 is 1. x2 transpose times x2 is 1. Which means each vector has a unit. So each vector has a unit length. Okay, so for x1 is unit length, x2 has a unit length. So the other one you can also do this. This one, if this is true, you can also say is x2 transpose times x1 is 0. They're equivalent. This is also x2 transpose times 1 is 0. Doesn't matter, you can just swap it. Okay. Alright. So that's the definition of orthogonal. For a pair of vectors, you can also define a set of vectors they are orthogonal. If vectors x1, x2, x3 they are orthogonal with respect to each other. If every pair is orthogonal, you sort of, if I draw a picture of that, you sort of can see somehow like this. So if I have, this is one of this, okay, this is another one, and this is last one. So they are perpendicular to each other. For example, if I have x1 is 1, 0, 0. Give example, x2 is 0, 1, 0. x3 is 0, 0, 1. So they are orthogonal with respect to each other. Okay, because x1, x2 they are orthogonal, x2, x3 they are orthogonal, and x1, x2 they are also orthogonal. Okay. Similarly for orthonormal, vectors x1 is orthonormal if every pair is orthonormal, then it's the same thing. So this one is also orthonormal. Okay. So now let's move to the matrix. So I talked a little bit about a matrix in the previous video. So matrix is a little bit general than vectors. So vectors typically only have one row or one column. So generally speaking, we're talking about column vectors, so we only have one column. But matrix, you have multiple rows and multiple columns. So row is given by row 1, row 2, row 3, so on and so forth. Column 1, column 2, column 3, so on and so forth. So the size of matrix is determined by the number of rows times the number of columns. For example, here we have 3 rows and 4 columns. So the size of matrix is 3 by 4. Okay. So the matrix plus minus product. So I don't talk about those ones. So matrix products is entry-wise plus, and matrix minus is entry-wise minus. The product is a little bit complicated. So let's give a little bit example of that one. So let's say 1, 2, 3, 3, 2, 1, and B is 1, 1, 1, 2, 2, 2. Okay, let's make it simple. Okay, so the matrix product must follow this problem. Let's say this is M times N. If I can do the matrix product, so which means the B matrix must have the size N times something. Okay, so these two values must be equal. These two must be equal in order to compute a matrix product. Otherwise, you cannot compute a matrix product. So matrix product, let's say here is so this is number of rows. So for A is 2, for example here is 2 by 3, okay, it's 2 rows and 3 columns. This is 3 rows, so 3 times 2. So the size of the product will be just AB. If I do that way, the product, the size will be just M times P. So, okay, the computation given by this, I'm going to briefly review that. Okay, 1, 2, 3, 3, 2, 1, 1, 1, 1, 2, 2, 2. So this is given by, I'm only going to compute the first number over here. So what it's going to do is you do the first row of the first column, first matrix, time first column. Okay, you do entry-wise product and you compute the sum. So you basically do this guy product entry-wise. So first one time the first one, second one time second one, last one time last one. Then you compute the sum. So it's 1 times 1. So this will be 1 times 1 plus, okay, is 2 times 1 plus 3 times 1. You do the same thing. For the second one will be the first row times second column. Okay, so this guy right over here is just the first row times second column. Okay, so this guy will be equal to the second row times first column, and the last one will be just the right over here will be just the second column times second row times second column. You do entry product, you do the sum. So I don't want to compute over here. That's how we do the matrix product. So I want to do the computation directly over here, but you can review some of the basic matrix operations by yourself. Okay, the next concept is the Neopotent. So Neopotent is a property for a matrix if it satisfies certain property. Okay, if a square matrix means, so here square matrix means the rows and columns have the same size. So it's an n by n matrix, which means it's the same number of rows. The rows column, the number of rows and number of columns, they are equal. So they call it square matrix. If a square matrix satisfies this property, a to the k, to some power, k of course is an integer number, positive integer number. It's 0, 0, 0, 0, all 0. Every entry is 0. For some positive k, so a is Neopotent. Okay, which means some power will become 0. A to certain power will become 0. For example, if I give you a 0, 1, 0, 0, so a squared will be a times a. Okay, you do the entry, the product, mixture product mentioned over here. So the product will become 0, 0, 0, 0. So a here, this matrix is a Neopotent. Okay. The next definition is a trace. The trace of a square matrix, so this is again a square matrix, is given by the sum of the diagonal entries. Okay, what is called diagonal entries? Okay, let me talk about a square matrix. A typically is given by like a11, a12, so on. So let's say the size n by n. Okay, so you have n rows and n columns. So diagonal entries is the number of rows and number of columns, they are equal. For example, the first row and the first column, the second row, second column, the third row, third column, so on until the nth row, nth column. So this will go, that's all called diagonal entries. So the trace of A is defined by the sum of the diagonal entries, which is also given the sum of the eigenvalues. We'll talk about eigenvalues later on. Okay? So trace, some of the property of the trace, first the trace A plus B will be trace A plus trace B. This is straightforward because A if plus another square matrix, so its diagonal entry, sum of diagonal entries will be the same, right? The trace of A times B will be trace of B times A. Okay, it doesn't matter. You can swap it. Okay. The determinant of square matrix. This is a little bit complicated. Determinant of square matrix is, let's say, first of all, it still means a square matrix have the same number of rows, same number of columns. The determinant of the matrix is, first of all, it derived from 2 by 2, then we go on to the 3 by 3, so on and so forth. Okay. Here's the kind of determinant of it. Determinant of 2 by 2 matrix is computed by, notation-wise, is you put two vertical lines of this matrix. You remove the bracket, and you put the vertical lines. Replace the bracket by vertical lines. That means the determinant. The determinant is you compute the product of 2 by 2 matrix is the product of diagonal entries minus the product of diagonal entries, which means, for example, it's 1, 2, 2, 1. So it's a product of diagonal entries. Diagonal entries are 1 and 1. So it's 1 times 1 over here, and minus the product of the off diagonal entries, which is 2 and 2. Okay, so 1 times 1 minus 2 by 2, so it's -3. So the 3 dimension for any higher dimensional ones is when you compute the determinant, you have to reduce the order 1 by 1. For example, for 3 by 3s, you first reduce the determinant to a 2 by 2, determine 2 by 2, then you compute the 2 by 2, then you find the values. Okay. So for any square matrix n by n, the determinant is given by the summation of aij. Okay, so aij is I and the j's entry of this square matrix. And j from 1 to n of Cij is the same as some Aij, Cij, when I from 1 to n. Okay, so let me give a little bit more detail about what this means. Okay, so if I give you the matrix A n by n is A11, A12, so on and so forth, A1n, and A21, A22, A2n, that's the second row until the last row AN1, AN2, AN. So Aij, of course, is each some entries over here. Like you pick a row or column, doesn't matter. This is when you pick a row, and this one you pick a column. Okay, so you can pick a row or column. So you just, for each of this one, you compute. Let's say you compute the second row. So this will be just A21, A22, A2n. You can pick any I over here. And then first of all, this is just the exact number coming from here. You put it over here. Then the Cij is the cofactor of Aij, which is -1 to the power of I plus j. For example, you say A21 is U2 is -1, 2 plus 1. Okay, let's see if we here C21 is -1 and 2 plus 1. Okay, determinant of A bar ij. So what A bar ij is, you remove you sort of remove the rows and the column that this entry is on. So you get a n-1 times n-1 matrix by removing the ith row and jth column of A. You get an n by 1. You sort of reduce the size of matrix by 1. Originally it's n by n. Now you have n-1 times n-1, and you compute the determinant of this. Okay, and you times -1 to the I. This is your cofactor. This is the cofactor. Then you compute for each of this one. You do the same procedure. For example, this is for C21. So apparently, for example, here, determinant of A can be written as A21 and C21 plus A22, C22 plus so on and so forth, so A22, A2n, C2n. So each of this guy is computed over here in like this form, and this is just each entry you put over here. So similarly, this guy, okay, can also be determinant. It can also be written as another form. It's determinant of A. You can also pick a column. Okay, let's say I pick the column here, right over here. So which means is A12, C12 plus A22, C22 plus so on so N2, Cn2. Okay, this guy is computed exactly the same way. Okay, as I mentioned, where you just use for different row and column. So here, this one you reduce by 1. So how to compute this one? You have to still compute this, right? This one, if this n is big, you only reduce by 1. So for each of this, you recursively use the same approach that I mentioned over here. You still have to do the similar one. For compute this, you go back to this method again. You reduce this further by 1 until you reach this 2 by 2. You know how to compute this directly. Then you can compute the determinant. So this is a very complicated process. Okay. For example, let me give you an example how we do that. For example, determinant of A is let's say A given by 1, 2, 3, 0, 1, 2, 0, 4, 1. Okay, the determinant, I can use the first row to compute the determinant. So it's actually this is A11. So this is A11. This is A12. This is A13. So I sort of have A11 C11 plus A12 C12 plus A13 C13. So A1 of course is 1. Okay, and the C11 here is this guy. It's -1 to the power of 1 plus 1, and you remove the first row and the first column, which is when this entry is on, right? First one, so you have 1, 2, 4, 2. Now this one I can compute is 2 by 2, right? This guy is 2, right? A12 is 2, okay, and C12 is here, is this all the stuff, okay? So -1, 1 plus 2, and you remove the row and the column that this 2 is on. So this is the first one, is remove this one, you have 0, 2, 0, 2, okay? So again, I can compute this is 2 by 2, I can compute it. Then this guy is A13 is 3, okay, then this is the whole thing is over here is just C13. It's -1 to the 1 plus 3, and you remove the row and column that this entry, this number 3 is on. So it's here and here, so you remove the remaining is 0, 1, 0, 4. So I can compute the determinant of this guy. It's just 2 by 2, right? It's given by here, so I can compute that. Now you can compute this one. You know, you can compute the number over here. So by doing this, I have this value. This is the first one, become this. This guy is 0 because 0 times 2 minus 0 times 2 is 0. 0 times 4 minus 0 times 1 is also 0. So these are gone. So then you compute is -6. Okay. So some properties we can say, if I give you a diagonal matrix, which means only the diagonal entry is 0, is a non-zero, and all other entries are 0. So this determinant of A is just a product of this all the diagonal entries. This also applies to upper diagonal matrix or lower diagonal matrix. So for upper diagonal matrix, which means your matrix this all 0, and only the upper, only the anywhere below the diagonal entry they are all 0. Above it can be non-zero. The determinant is again given by the product of the diagonal entries. This also applies to the same property, also apply to the lower diagonal entries. You say if I have A11, A1, A22, so on, so A and N. So these are all 0. Okay, this is you have specific numbers A21, so on so forth, A01, so on so forth. This can be non-zero. This again, the determinant of A is the product of diagonal entries. Okay. All right. So the next one is determinant A times B is determinant A of determinant B. That's a property for the determinant to matrices. If A and B are square matrices, of course they must be square, otherwise it cannot compute this. Okay. So next one is, what is the inverse of a straight matrix? Okay, the inverse of straight matrix first has to be a square matrix. So for a matrix n by n, if A times B is B times A is equal to identity matrix, for some matrix B is also a square matrix, so B is called inverse of A. So identity matrix is defined by is a matrix which only has non-zero entries on the diagonal entries, and in particular the diagonal entries are all equal to 1. Okay, so all other 0. The identity is always like this, is 1, 1, 1, 1 on the diagonal entries. The other part will be just 0. Okay, so if that's the case, we saw that the B is called inverse of A. Okay, if A inverse exists, we can also say the determinant A must be non-zero. Okay, so how do I compute the inverse of matrix A? So there are two typical ways we can compute the inverse of A. First one is called Gauss-Jordan elimination method. So what you do is you first put your A and your I. Okay, this is identity matrix. Identity matrix. All right. Then you apply row operations only to both. So you use the dashed line, the vertical line, to separate the A and B. Okay. So the goal is I want to do operations such that my left hand side of A become identity. So what you do row operation. You do, let's say, row sum, row scale, and row even swap a row. That's fine. Then until you change your A, the left hand side of this dashed line become identity. Now whatever right hand side become, you do the same operation for both sides, of course. Then right hand side will become A inverse. Okay, that's called Gauss-Jordan elimination method. So the other one is called a determinant approach. So for example, a matrix, a 2 by 2 matrix inverse is 1 over the determinant of A. So I already talked about how to compute the determinant right over here. This is for 2 by 2 matrix, determinant how to compute that. So the determinant is 1 over the determinant of A times the cofactor. So this is C11, C21, C12, C22. So pay attention to the relationship. This is not C12, this is C21. Okay, so it's C11, C21, C12. So it just is a different order. It's not C12. Okay, you swap. This is Cij is the cofactor I mentioned right over here. So when you compute cofactor, don't forget about this negative sum to the power of this cofactor. Okay. For the 3x3 matrix is also 1 over determinant A times C11, this is C21, C31, C11, 12, C13. So if you can sort of see the order is transposed, right? The right order should be C11, C12, C13 if you kind of remember what you define that, but it's just a transpose of that. Okay. You can also see is ANN times N inverse is 1 over determinant of A. And the time here is C11 and C21 times Cn1. This is C1n, C2n, so on and so forth, Cnn. Okay, so that's the same way you compute the inverse. Okay. So next one is the eigenvalue, eigenvectors. Okay, they also talk about the property for a square matrix. Okay, if I give you a square matrix, okay, which is an by n, if a time a vector, this is vector, is equal to lambda, lambda is a scalar time this same x, x is a column vector, and lambda is scalar, so lambda is called eigenvalue of A with an associated eigenvector, eigenvalue of A with an associated eigenvector of x. For example, if I give you A is 0, 2, 0, 0, 2, if I do A times 1, 1, okay, this x is 2, 0, 0, 1 times this is x, okay, 1, 1. So if you do the product, 2, 1 times 1, 0, so it's 2, 0, 2 times 1, 1, 1 is 2, so it's 2 is 2 times 1, 1. So you sort of can say, hey, A times x is 2 times x. So I can see this is the eigenvalue and this is the eigenvector. Okay? So the property of eigenvalues, the determinant of A is given by the product of all the eigenvalues. Okay, product, this means the product. Okay? So how to solve for the eigenvalue, eigenvectors? Okay? So if I give you a matrix A, the eigenvalues of A is computed by solving the equation which is given by determinant of A minus lambda I is set to be 0. Okay, which means if I do right over here is determinant of A, which is 1, 3, 0, 2 minus lambda. Okay, I don't know what lambda is, that's why I have to solve for it. Identity is 1, 0, 0, 1, this identity matrix. Okay, you set to be 0, you find what lambda will satisfy this property. Okay, what I do is to put them together is determinant of, let's say over here is 1, 3, 0, 2. You first compute lambda. This is lambda 0, 0 lambda. Okay, you set to be 0, and this is a determinant of 1 minus lambda. Okay, 3, and this is 0. This is 2 minus lambda. Okay, so what is the determinant of 2 by 2 matrix? I talked about it already. So determinant of 2 by 2 matrix is the 1 minus lambda is the product of diagonal entry minus the product of time is 0 times 3, right? 0. So this will be gone. So it is 1 minus lambda times 2 lambda equals 0. So which is 1 lambda 2 minus lambda, you set to be 0. Okay, so the solution will be lambda 1 is 1 and lambda 2 is 2. So they have two eigenvalues. Okay, so this determinant of A minus lambda equals 0. You can also say determinant of lambda minus A. It doesn't matter which one you use. It's the same as determinant of this. They are equivalent, basically. This one is also called characteristic polynomial. You set it to be 0, you find a solution. That will give you the eigenvalue of the matrix A. Okay, so I'll stop with here and talk a little bit more about eigenvalue, eigenvector next time.